if we really want to understand muscles, we need to look deep into the microscopic world. And that's what you're seeing right now. You're seeing a sliding filament of muscle, and that's what this lecture is about. We have these two filaments, actin and myosin. Calcium is going to attach to troponin, and when that happens, we get a shift. And that shift is huge because now tropomyosin is going to move, and look at that myosin head, it's going to bind. Now right there, now this may not make sense to you, but that binding is how muscles move. Alright, so let's stop this for a minute. So here we have Danielle, one of our healthcare professionals, showing us a stretch. But muscles don't really stretch. What happens is myosin is going to walk its way, or you could use a rowboat idea, it's going to row its way along the actin. How does this happen? Let's find out. First, let's just look at a muscle fiber. It's filled with this sarcoplasm. Take a look to the upper right. Sarcoplasm, I hope you're getting the idea that that prefix sarco is something to do with muscles. It's surrounded by a sarcolemma right here. Now, so there's some diseases where this sarcolemma is going to tear, but if you don't have a disease, then it's a nice sheath around this bundle of myofibrils. There's also a carbohydrate called glycogen, which I'll say more about later. It's a compact form of sugar, and we have it in our muscles. It's like your own natural energy drink. Anytime you get tired, forget about the Red Bull or whatever you want to drink. Just wait for your glycogen to start breaking down into sugar, and then you're set. Myoglobin stored in the myoglobin. I'll talk about that later too. That's see the globin? Myo is muscle, globin. It's a red protein that binds to oxygen, and I'll talk about ATP shortly. ATP is the smallest form of energy used by cells. You see, even though we have glucose, it's too big, and so it's broken down into the smallest packets of ATP, almost an electric energy. Sarcoplasm I've talked about. There's myofibrils, and their myofibrils have thick filaments and thin, and you're going to hear that word over and over again. Thick is the myosin, thin is the actin. So there's those words, and you're probably going to see those words like 20 more times. And by the end, I hope it makes sense. The sarcomere is the functional unit. So each one of these sarcomeres, if you look lower right, this is the contractile unit. And so you have one after another after another. Muscles are made of all these contractile units. It's not like one slab of steak has just ropes of muscle. It's all really organized. Let's look at the structure of the sliding filaments. There's these thick myosins, and the way I remember it is thick has more letters than thin, and actin is a shorter word than myosin. So myosin, thick filaments, actin, here's the word, thin filaments. Alright, so the regions are, there's an A band, which is the thick length of myosin, the whole length. There's an I band, which is the thin filaments that doesn't overlap with the thick. And you might think, well, who cares? You know, overlap or no, not overlap. Well, no, it does matter, because you're going to see these guys slide back and forth. And then the H zone is where there's only thick. So you're going to see in the middle thick. And down the middle is the M zone, which you can see the lower right. And this is an actual micrograph, a photograph of muscle. So you can see the sarcomere from Z. Z is an anchor point to Z. And there we have it. Midline on this sarcomere. And here's another sarcomere with midline. And on it goes. I talked about these contractile proteins, actin and myosin. And there's a regulatory protein that's going to switch muscle contractions on or off. And there's a site here that it's a myosin binding site. But if you look here to the right, you'll see this tropomyosin, this rope-like structure, is going to block the binding sites. And so this myosin would like to make contact with the actin. And if you think myosin has heads, actin has action, because actin's going to slide. Okay, so there's also this, I don't see the word here, tintin. Yeah, here, oh, here it is, okay, tin. It's a little elastic protein here that's going to keep the fibers from tearing. So it's connected here to the myosin, and then actin on either side. Nerve impulses, so here we go. We're gonna actually make this muscle contract. There's a nerve impulse. It's going to go down the spinal cord, and there's the neuromuscular junction, and we're going to have the sarcoplasmic reticulum, which surrounds the myofibril. So see this little lumpy, whatever you want to call it, that's the sarcoplasmic reticulum. It's going to release calcium, and calcium is going to flow into sarcoplasm, the fluid, and then it's going to bind to actin. So take a look down below. Here's the actin. I talked about tropomyosin covering the binding sites. You see those little holes? It's covering them. But when calcium, there's a calcium binding site as well on the troponin, and it's going to cause the tropomyosin to shift to the side. You know, it's kind of a good idea. I mean, think about it. It's like having your door closed. You don't want any company, you close the door. So you got tropomyosin closing the door. But hey, you're going to have a party? Get some calcium in there, and then we're going to open the door, and we're going to see something happen shortly. We have different views here. This is an in view. This may not do anything for you, but I just thought I'd throw it in there. And here's the side view. And there's the rowboat idea. So calcium binds to troponin. I've talked about that. Tropomyosin is going to shift. And when it shifts, now the myosin binding sites are exposed. So the open door, time for the party. And we get a cross bridge. So look down below, lower left, you'll see a cross bridge forming between the myosin head and the actin fiber. And you see this little thing, ADP. Well, it takes energy to contract a muscle. And ADP is a low form, but we're going to get an ATP shortly, and that's going to drive the power stroke. Okay, I made this little drawing just because I thought it might help. It may not help you at all. Here's the actin. There's the binding site. There's a myosin head. And we are ready for action. So this is all happening inside the myofibril, upper right, because I don't want you to get lost. Like, what is he talking about here? Well, here you have a cross section of a muscle fiber, and you can see how it's there's these myofibrils, and the myofibrils have actin and myosin. Okay. There's a cross bridge binding myosin head, because calcium is going to initiate this exposure of the binding site. And the drawing to the right, of course, is much better than mine, but sometimes I like simple things. So there's the shift, and there below, lower right, you can see the opening of the myosin binding site because tropomyosin has shifted. Yeah, okay. I told you you'd see these words at least 20 more times, actin and myosin. Now, let's say we have Danielle here is going to flex her muscle. Then what we have is a power stroke. The myosin head is going to tilt towards the midline, the M line of the sarcomere, and when it does that, it's going to push actin that direction. Do you remember that rowboat idea? So if that helps you, think of like a rowboat. The actin's like the water, myosin's like the paddle. It's going to push it down. Sliding filament. Do you see that? So muscles don't stretch. They don't. I mean, there's a little bit of stretching in the tentin fiber, but really muscles slide back and forth. There's detachment because ATP is going to drive the power stroke. So when new ATP is released, and that's why when we work out, need calcium, of course, for the binding site, and then we need energy in the form of ATP. Where does that come from? Well, it comes from what you eat. Or it's broken down from the glycogen in your muscles. And if you're in good shape, you don't need to eat or drink any kind of beverages while you're working out. You just let your muscles leak ATP right into themselves. Okay, it's the people who are out of shape that have to drink all those energy beverages. All right, and here we go. Nice little review. If I can get this thing to come up. Cool. There it is. Okay, well that one's firing up. Let's take a look. ATP is the energy source, and the sarcomere is the unit of contraction. I talked about ADP. So ADP is becomes ATP. Do you understand? So you have adenosine diphosphate. You don't have to remember that long word, but when we add a phosphate, now we have a triphosphate. That's high energy, but that ATP is going to be used up during the power stroke down here. And when that happens, then we get the low form ADP plus P. So it's a cycle. ATP, ADP plus 2. Low energy, high energy. Okay, to the right, let's take a look. We can get a little review going here. Here's the sliding filaments. So that must be myosin, the pink. You see there's the rowboat concept. And there's the actin, the thin filaments. They are a little bit thin. We take a closer look. There's the myosin heads. And they're going to need some ADP, right, at some point. There it is, ADP plus P, because that's going to be ATP shortly. There's the actin, and you can see the tropomyosin and the troponin. I know this is all confusing. What is this stuff? Got to be calcium, right? Calcium coming from the Sarcoplasmic Reticulum. It's going to bind to actin. And watch, tropomyosin should slide. Hey, come on, slide. Well, we know it should slide. Remember, it's going to slide and expose the binding sites for the myosin. Okay, now pretty soon we should see ATP coming because this is low energy. What's the hold up, guys? There we go. Oh, power stroke. Okay, is this starting to make sense? Well, give it your best. I think if you get this basic concept, upper right, these guys, and get the idea of the tropomyosin, the troponin, cross bridge, it'll start to come together for you. First time around, you might think I'm just telling you something crazy. All right, good luck studying this. Thanks for listening.